Yep. Hi everyone. So I'm going to be talking about fluorescent minerals, which is one of my favorite group of minerals to talk about and look at and find and study, just because they look super cool under UV light, like the background picture is showing. So let's dive into fluorescent minerals and what makes them fluoresce. So, overview, kind of what we're going to talk about is background, how does fluorescence work, shortwave versus longwave, fluorescence and minerals, which minerals fluoresce, fun facts, including field applications, and then other types of fluorescence, because there are other subcategories of fluorescence. So, background, all minerals have the ability to reflect light. However, only some minerals have the ability to fluoresce. And so when we talk about fluorescence, these minerals are temporarily absorbing a small amount of light and then releasing the small amount of light of a different wavelength. So light's coming in at a certain wavelength, these minerals are absorbing it, but then the light they're releasing out is going to be a different wavelength. And the change in the wavelength is going to cause a temporary color change to the human eye. So light comes in, hits the mineral, and is then going to come out at a different wavelength, and we're going to see a color change in the mineral. So that's what we're observing. And these are most spectacular to view in a dark room using UV light, just because you're going to get to see the best fluorescence by doing that. So how does fluorescence even work? Well, you need a proper light source, so typical light sources for fluorescence involve UV, like ultraviolet, which is illustrated here, X-ray, and then cathode ray. And with UV, X-ray, cathode ray, they need to have the ability to excite an electron within the atomic structure of the mineral. And so like here we have, our atom, we have our nucleus, we have our valence electrons. So the light source that we're using needs to be able to excite at least, one of these electrons and have the ability to cause that excitation. And the excited electron will temporarily jump out of place to a higher orbital within the atomic structure and fall down to its original orbital. And that process that occurs will release a small amount of energy in the form of light, which is the fluorescence. So basically what we're seeing happening is we have our excitation energy. So we have like our UV light source, for example, is going to come through, is going to hit our valence electron, and it's going to get really excited. So it's almost like when we have like a sugar high or a caffeine high, we're very energized, very excited. And so that electron's going to be very energized, very excited. It's just had, its first cup of coffee for today or first cup of tea, and it's going to get kicked up to a higher energy state because now it's like really excited. However, then the electron is going to drop down to a lower energy state, so that excitation is going to wear off. So kind of like our sugar crash or our caffeine crash is just going to wear off. It's going to come back down to its original orbital, and there's going to be an emission of light that comes off of that. And that emission, that small amount of energy, is going to be what we see as fluorescence. So that's kind of how fluorescence works. And the wavelength released is often distinctly different than the incident or the initial wavelength. And so this is going to produce a visible color change of the mineral, and the mineral is going to sort of glow this color as long as it's illuminated with the specific light source. So like in this image here, we have these specimens and they look a specific color, whereas under the UV light source, they're now looking like a completely different color. So their physical properties are still there. So like the stripes that we see in both images are still present, but the coloration is significantly different. And then there's also shortwave versus longwave UV light. So the difference in wavelengths in nanometers. So like shortwave is around 254 and longwave is around 350 something nanometers. And so the difference in wavelength can also cause a significant color change with fluorescence. And so shortwave is present in sunlight, it's high intensity, and it can cause sunburn and eye injury, which is kind of why, we don't look at the sun. And it's around 254 nanometers, whereas longwave is low intensity and is around 365 nanometers. And some minerals will fluoresce the same color under both wavelengths, others will fluoresce under only one wavelength, and others will fluoresce different colors in different wavelengths. So it's very dependent on the mineral and the elements present in the mineral, as well as atomic structure and other things. So there's a lot of stuff that goes into determining how a mineral is going to fluoresce. And many minerals are going to fluoresce under shortwave UV light. So let's talk about fluorescence in minerals, because that's the whole point. That's why we're here. So fluorescence in minerals occurs when the mineral is illuminated by a specific wavelength of light, and most minerals don't have noticeable fluorescence. So only about 10 to 15% of minerals have fluorescence that is visible to humans. So we're only seeing 10 to 15% of the total fluorescence that is occurring with minerals. The other fluorescence that's occurring is not enough for us to be able to pick it up with our eyes. And even of those 10 to 15%, not all of those specimens are going to fluoresce. And it's because we need activators. So what is an activator? So activators are impurities present in the mineral that cause a mineral to fluoresce. So if we want fluorescence, we want a mineral that is not pure. And activators can include cations of the metal, they can include rare earth elements like REEs, and they can include crystal structure defects, they can include organic impurities. And there's also cons of these impurities. So some impurities will have sort of a dampening effect on fluorescence, and examples of that are iron and copper, because they can reduce or eliminate fluorescence. So if we have iron or copper in our mineral, then the chances are the mineral is not necessarily going to fluoresce as well, or even we might not even see the fluorescence because of the presence of iron and copper. So which minerals fluoresce? There is a long list of minerals that fluoresce. And then there's specific minerals that I want to talk about just because they're the ones that I think are the coolest, in my opinion. So there's a website which is linked down here, but they kind of categorize all the minerals based off of their color under shortwave and longwave fluorescence, and even include links so you can go click on them and view them and look at them. And it's really cool. It's a really helpful website. So I'm not going to go through the entire thing of it, but basically I would recommend checking it out if you're interested. But there's shortwave, and then we get into long wave, and so now we're into long wave with the same coloration breakdown, and short wave, or long wave, sorry, long wave. So let's talk about Hacmanite. So Hacmanite's formula is right here. It is a sulfide-rich sodalite. It's from the silicate family, and its most common activator is the sulfide, so S2-, which substitutes for the chlorine in the formula. And invisible light is going to be a pink to gray, white to white color, and it kind of looks like, I guess, kind of like this in visible light, but in long wave UV light, it's orange, and in shortwave UV light, it's an orange-yellow color. So at the end of this, I'll show you all what Hacmanite looks like under UV light. And then we also have scapolite. So scapolite is from the silicate family as well. Its most common activator is iron 3+, and it does have other activators such as lead, sulfide, europium, and oxygen. And invisible light is going to be a white, gray, colorless, cream, yellow, bluish, gray, purple color. So kind of looking like this in normal light. And then in long wave UV light and short wave UV light, it's going to vary in color. So this one is one that will fluoresce, that can fluoresce different colors depending on the UV light used on it. And then we have fluorite, because fluorite is the original fluorescent mineral. So we have to talk about fluorite. So fluorite was discovered to fluoresce by George Gabriel Stokes in 1852. And George Gabriel Stokes is a physicist and a mathematician. And he noticed fluorite's ability to produce a blue glow when illuminated with invisible light. And when he said invisible light, he was referring to UV light. And he named fluorescence after fluorite. So fluorescence gets its name from fluorite. And so fluorite is has very short chemical formula, but its most common activator is europium, though it does have other activators, and the one that I think is the coolest one is organic impurities, because I wasn't expecting that to happen. But visible light, it can be all colors basically, but pure fluorite is colorless. And then in long wave and short wave UV light, it's going to fluoresce blue. And some fluorite specimens actually have such strong fluorescence that you can hold them out in the sun. And then when you bring them into the shade, they will actually show a color change because their fluorescence property is very strong. And so I think that's really cool about fluorite that you can do that, because the other minerals you really can't, but fluorite, that's pretty cool that you can do that with fluorite. So here's fluorite and what fluorite looks like in normal light. And then we have willemite, which is also really cool. And it's part of the silicate family, and its activator is manganese. And invisible light is kind of like a brown, reddish brown, green, white, gray color, but in long wave and short wave UV light is going to be a green color. And so this is what willemite looks like under UV shortwave. And I think it is really cool that it goes from looking like this to that, because that's completely unexpected and it looks super cool. And the coloration kind of reminds me of slime, and I don't know, so it looks cool and makes me think of slime. And then we also have rhodochrosite. So rhodochrosite, manganese carbonate. So it's part of the carbonate family. Its most common activator is manganese 2+, where it also have other activators. And invisible light is going to be like a white or a pink color. And in long wave UV and short wave UV, it will fluoresce red or pink. And so this is kind of what it looks like under UV long wave. So it's not a substantial difference. So it's not kind of like a shocking fluorescence change with rhodochrosite, but it's still pretty cool that we kind of get a more deeper red under UV light than we do in normal light. And then calcite. So calcite is calcium carbonate, and it's part of the carbonate family, and its most common activator is manganese, though it does have other activators, including organic impurities. And invisible light, it's colorless, white, pink, yellow, brown. But in long wave UV light, it can be pink to red, and in short wave UV light, it's going to be blue. And calcite can actually fluoresce all the colors. So what's really cool about calcite is you don't know what color it's going to fluoresce until you actually get it to fluoresce, which is really cool. It's kind of like the mysterious fluorescent mineral. So, and this is kind of what it looks like. So invisible light, we have this UV long wave, and then short wave. So you can get different colors using different UV wavelengths, and you also get different colors in different types of light situations. So that's really cool about calcite, that you never know what you're going to get until you actually try it out. And then there's aldanite. So aldanite's formula is up here, and its families include phosphate, arsenates, and vanidates, and its activator is the uranyl ions. So this one right here. And invisible light is a lime green, and then under UV light is going to be a bright green. And so this one looks really cool. So even though there's not a substantial difference, the bright green gets a lot more like brighter under UV light, and so it's a much more like stronger, brighter green color, and it looks really cool. And so what are some fun facts about fluorescence? So one fun fact is that there are fluorescent geodes. So geodes that have fluorescent minerals inside are obviously going to fluoresce. And an example are the Dugway geodes that were found near Dugway, Utah, and they contained a chalcedony, which fluoresces a lime green color due to trace amounts of uranium present in there. And so this is what it looked like under UV light. And what's really cool about these geodes is that they formed millions of years ago in pockets of a rhyolite bed, and then 20,000 years ago were eroded away by wave action along the shoreline of a glacial lake and transported, and now they're found with lake sediment. So that's really cool. And if you have a geode, or if you find a geode and you break it open, or it's already broken open, you should see if it fluoresces, because you never know until you try. And tungsten ore. So tungsten ore will display a distinct blue fluorescence. And so this is kind of what tungsten ore looks like in visible light. And this is what it looks like under UV light. And so miners and geologists can use this to their advantage. And so they can use the UV light at night to locate where the ore is at. And they'll generally find it in scheelite, which I wrote its chemical formula there. And tungsten ore is used to make filaments for fluorescent light bulbs. So tungsten ore is kind of like full circle in a way. They can use UV light and use its fluorescent properties to find it, and then it gets used in fluorescent light bulbs. So full circle with tungsten ore. And then in the oil and gas industry, so geologists will sometimes examine drill cuttings and cores with UV lamps. And the reason why is because there are small amounts of oil and mineral grains that are stained by oil, and those will fluoresce. And the color of fluorescence will indicate the thermal maturity of the oil. So darker colors would mean that you have heavier oil present, whereas lighter colors are going to mean you have lighter oils present. And so I didn't know this, and I think it's really cool that they can do that and use that to figure out at least like whether there's heavier or lighter oils present. So that's something that I didn't know that I thought was cool. And there's also selenite crystals. So in the Great Salt Plains in Oklahoma, so if you're in Oklahoma or if you're going to visit Oklahoma, you should go to the Great Salt Plains because you can basically dig up like 10 pounds of selenite crystals and keep them, and then you can go and see if they fluoresce. And so basically they're double terminated selenite crystals which show moderate fluorescence and phosphorescence under UV light, and we'll get to phosphorescence in a little bit. But under long and shortwave UV light, they'll show a warm tan and pale blue fluorescent color, whereas under shortwave phosphorescence, it'll kind of be this bluish green color, and then under long wave phosphorescence, it'll be green. So this is what it looks like in visible light. This is what it looks like under UV. And then phosphorescence, this is what it looks like. And the cool thing about the selenite crystals is only the ones that have the perfect hourglass shape are going to be the ones that will fluoresce or phosphoresce. So if they don't have a perfect hourglass shape, it's not going to happen. So that's something to bear in mind when you're looking for your selenite crystals. If you want ones that are going to fluoresce, you want the perfect hourglass shape. And there's also other types of fluorescence. So what we just talked about was phosphorescence with selenite crystals. So phosphorescence is a delayed release of electrons from higher energy levels, and the release can occur for a few seconds to a number of years, depending on the situation. And the result is that the mineral glows even when the UV light source is turned off. So we have our fluorescence that occurs. And so, we've excited the electron, it's had its, daily dose of caffeine, or it's on a sugar high, and it's really excited, and then it crashes down, and that's fluorescence. Whereas with phosphorescence, we excite it, so it's really excited, but then when it decides it's going to come back down and it starts experiencing that crash, it's more like a slower crash. So it's just going to take its time as it's crashing down to its original orbital, and that delay in time of coming down is what is known as phosphorescence. So instead of the rapid bam, I've just crashed back down, it's just gonna slowly take its time and be kind of really chill about it, and then it will land back to its original orbital. But during that slow, chill time, we're seeing phosphorescence. And so I have two videos which show phosphorescence in action. So if you don't have a mineral that phosphoresces, you don't have a mineral that fluoresces, you can get phosphorescence to occur by using spearmint. So if you can go to like your local grocery store, just any store like dollar store, you can get a bag of spearmints and try out phosphorescence with them, and it's really cool to do. So this is what I did with spearmints and UV light. And so let me play. Oh, that looks so bad. Hold on. Well, let's see. We're just gonna play this one first. So the UV light's on that one, and then we're gonna shut it off, and it's still glowing afterwards. So that like delay and glow as it slowly faded away, that's phosphorescence. So that spearmint, it has the property of phosphorescence, which is really cool. And then I tried it with crushing up the spearmint. So I took the spearmint and broke it up using a hammer, and wanted to see if phosphorescence was any different with a whole versus a broken up spearmint. And the results were pretty similar, but we can look at it. And so it's still phosphorescing. So even though I broke it up, it's still phosphorescing with the UV light getting shut off, and it's still glowing. So yeah, so spearmints can also phosphoresce. And then there's also polarized fluorescence. So this is often in calcites, And you illuminate mineral with UV light and view the mineral through a plane polarizing filter. And then you can rotate 90 degrees, which will show zones in the crystal that alternately brighten and darken. And light is getting emitted through that because the electric fields of their activator atoms are aligning to each other and to the axis of the host crystal. And I didn't want to go back. There you go. And then there's also thermoluminescence, which is involving a heat source, and then cold temperature fluorescence, so we want to keep it cold. So with thermoluminescence, you can hold a mineral under hot water or heat it in an oven. I would recommend doing that under supervision if you're going to try that out, just because of safety purposes. And it will glow much more strongly for a period of time, and that also is very dependent on the mineral as well. So thermoluminescence does not work with all the minerals, so if that was something of interest, there are specific minerals that will fluoresce better under thermoluminescence. And then there's also cold temperature fluorescence. So scapolite and some feldspars will fluoresce more strongly when they're chilled. And you can test this by observing their fluorescence at room temperature and then chill the mineral in the freezer for a minimum of 2 hours and see how that works. You can also pack them in dry ice as well to test that out, but also that would be recommended to do under supervision just because of safety and to follow safety procedures for dry ice or for that. And then there's also triboluminescence, which is one of my favorites. So like my 3 favorites are fluorescence, phosphorescence, and triboluminescence. And triboluminescence is when minerals glow when they are crushed, scratched, or rubbed. And these minerals contain elements or other agents that will emit light when mechanical energy is imparted to them. So when you crush them together or like whack them together or like scratch them together or rub them together, that energy is going to cause this light to appear. And so examples include calcite, fluorite, lepidolite, sphalerite, some feldspars, and then clear quartz. And so I have a video that we're going to look at, but basically it's going to be all about with the clear quartz. And so this is kind of what clear quartz kind of looks like. And if I were to whack clear quartz together with another piece of clear quartz, so kind of like, I guess with like the top parts of these pieces, then I will generate this sort of flash of white light. And what's happening is the mechanical energy is causing that to occur. So I'm causing electrons to get displaced by whacking the quartz together. Whereas I have these quartz, which isn't really clear. It's more of like this cloudishy, whitishy color. And if I were to whack that with this clear piece of quartz, it's not going to happen. And I'm not going to see triboluminescence with it. So it only works with clear quartz. And if you do try and whack things together or rub them together or scratch them together, I recommend wearing like safety goggles or like keeping it away from your face just because fragments do fly off. I've cut myself a lot with doing the quartz as well as gotten fragments flying into my face. So safety first if you're going to try that out. But let's watch the video and see how that works. Oh wait, did it just end on me? Oops. So there we go. So there's a glimpse there. And then there's one over here. And those there, so around this area. And there it is. So it's kind of occurring up there. So those flashes of light that we're seeing are from the 2 pieces of quartz being whacked together in the dark. So you have to do it in a dark area just because you won't be able to see it if you are in a well-lit area. So if I were to do it in this well-lit area, you wouldn't see the triboluminescence occurring. And so we can also look at this. So I said before that we were going to look at fluorescence ourselves. So I am going to go turn off the lights and stop sharing my screen. And we can look and see some things fluoresce. So let's do this. Okay. And my computer's gonna light up my face, so we're gonna change the camera angle so that way we can actually see this fluoresce rather than looking at me. So let's change the camera. So let's see. Okay. So what I'm gonna do is put in let's see. Let's look at Hackmanite. So I have Hackmanite. It should be around here. So here it is. And basically this is what it looks like under UV light. So it kind of has that orangey color going off on it. And then I'm gonna switch the type of UV light. And so now it's changed to kind of be more so like a redishy orange. It's not showing up super well on the camera, but it's kind of like this orangey, redishy, pinkishy color. And then we can switch and look at another one. And so let's look at scapolite, which is one that we talked about. And so this one kind of looks like that, and then kind of like this orangey, yellowishy color. So there's scapolite fluorescing. So I'm going to shut off the light. So this one doesn't do any phosphorescence. So even with the UV light on, turn it off, and now it's gone. And we can also look at fluorite. So we have some fluorite that we can look at. And so this one is going to be fluorite. And so it's kind of fluorescing like this blue color. So this is fluorite fluorescing, and remove the light and it's not phosphorescing. So fluorite is only fluorescing. And then another one we can look at is coal. So I have a piece of coal, and what's really cool about it is it actually has specks of it that will fluoresce, which I thought was super cool to sort of see. So kind of like these glowing specks. So in this one, it's kind of more of like a white-ishy color. So, I guess so it's kind of like this whitish-y color there with its specks like that. So that's coal, and coal is actually fluorescing, which is really cool. And then we can try it with this light and sort of see the difference. And the difference is this now is kind of fluorescing this blue color. So you see the specks are kind of now more so a blue color. And so now we have these blue colored specks. And so that was kind of it for talking about fluorescence and minerals. And I hope you all enjoyed it as much as I did, because I love talking about fluorescence. It's so much fun. And yeah, I'll see you all next time.